microstates. Okay, thank you very much. Let me start by thanking the organizer for putting together this workshop in a wonderful location. So it's always great to be back in Trieste. So what I will discuss today will be, I think, very reminiscent of what Manuela has been presenting before earlier today, and for those of you who attended Cristoforo's Journal Club, what he was discussing yesterday. And I will try to, along the way, to stress when things are different in the setup I'm considering. The main message is that the standard techniques that people studying GR been using for a lot of time, and this is the black hole perturbation theory. So the idea of starting from a nice solution that is rich enough to contain physical information, but easy enough that allows you to calculate explicitly and perturb this solution. So that's what we will be doing. Can also be applied very successfully in an holographic context. And that's this for microstates. So it's kind of putting together maybe two not immediately connected fields. So we started focusing on this in the context of the ADS-CFT duality, and in particular ADS5 cross S5 dual to n equal 4 super Yang-Mills a couple of years ago. So this is a first paper that that we had with Francesco Prila and Stefano Giusto. And what I want to do today is also report on some follow-up progress that we have. And the key novelty you will see is this Kaluza-Klein mode, so having a richer structure on the CFT. So I will focus on something that is work in progress. So it's maybe a bit strange because I'm talking about a second installment of a paper, and I will tell you nothing about the first one, which already appeared. The reason for that is that today I will focus on the gravity side. And the first paper, I maybe just mention it to use some results, was entirely on the CFT side using bootstrap. So that's kind of two different approaches, and of course the goal is to show that when they are in an overlapping region of validity, we get the same result. Very good. So while I'm doing this and focusing on this geometric setup, I'll try to provide some useful comments for talks that are coming up. So one is Carlos' talk on Thursday that will focus on a very different system, but the technology will be the same. So that's something I would like to stress, that once you learn to do to use this technology for one problem, for almost for free, you can apply to the other problem. And then I think Francesco Prile next week will talk about kind of another an observable that is very closely related to what I will present today. So I'll try to also highlight connection with what I think he will be doing. So the starting point is some classical solution. So think about this as some metric. So since we are talking about black hole, we will be focusing on gravitational theory. And so this will be kind of generalized. It does not need to be a black hole solution. It can be a more complicated solution or different solution, but there will be some metric. And think about the two main applications are pure GR, and this is what Carlo will be discussing in coordination. And what I will be focusing today is type 2B string theory. I will be entirely working in the Sugra limit. But maybe Francesco, starting from the CFT side, will go, I think will go beyond that. So we have a metric here, and the word perturbation is the idea of studying some extra field. So you can, in this setup, I'm considering here, it will be really a scalar field, another field. And you will perturb your background by adding this field. And you want to solve some wave equation describing how this perturbation behave in that background. So the approach, the idea is that this M, I will call MH to stress that we think about this as a heavy object. And the fact that we have a classical solution is that we will not neglect this quantity. We can think about this as some kind of Schwarzschild radius. So in the idea is that this metric describes a heavy state. In the n = 4 dual, so I'm repeating things that already appeared in Manuela's talk. The idea is that this G is 1 over n squared, where this is SUN gauge theory. And this M is the conformal dimension. Right here I'm thinking about M in the units of the ADS radius. So this becomes like the conformal dimension. And if we want this curvature to be of the order of the ADS curvature, so to be order 1, we cannot neglect it as a small object, right? That's the scaling. So this type of geometries will be describing operators in the dual theory that are not elementary gravitons, elementary dilatons, right? But will be operator was conformal dimension scales with n as n squared. Right? So this is the heavy operator that Manuela mentions. So these are heavy operators. Very good. So what I will be doing differently from the discussion of this morning is that I will not impose, if you wish, thermalization to start with. Actually, I'll do the exact opposite. Instead of using ADS Schwarzschild as the ground of this metric here, I will choose one of the LLM geometry. So this will be one of the LLM geometries. And the idea is to choose a geometry that is simple enough that allows you to do calculation, but has a precise dual description in n = 4 that we know.
Can I ask?
Yes.
If you start with LLM, how do I know that this is not some type of giant graviton?
Yeah, that depends the number of boxes that you have in your Young diagram, right? So if the number of boxes scales with n, then it's still a heavy operator, but it's not heavy enough to backreact on the geometry. So the type, this scaling here is telling you that you have the black region, right, of the LLM plane when you pixel it as n square pixels, right? So at that point, you cannot neglect the back reaction. Right? Yeah, that's an important point. Very good. So this solution was already known in a series of couple of papers that Pop and collaborators in 2004, I think. And maybe let me give you an idea of what this solution looks like. So is a 10-dimensional metric because it's type 2B supergravity. And you can factorize it in two structures. So this is a deformation of ADS. And this is a deformation of the sphere. And the metric, and also the fine form, which I will not talk about, are entirely determined by a single function which takes this form. So here Q1 is a non-negative parameter. If you set Q1 equals 0, this becomes a perfect square, and then the 1 over r square cancels. This H1 becomes 1. And this metric becomes empty at S5 plus S5. So just to give you an idea, maybe these are only a few formulas I will write. So this H1 becomes 1, F becomes 1 plus r squared, and you can see ADS in global coordinates, 1 plus r squared, and then dr squared divided 1 plus r squared. So Q1 is the object that tells you that, the parameter tells you that this it becomes a non-trivial state. And the mass of this state depends on Q1.
Can I ask another
Yeah,
question?
sure.
What is the supersymmetry preserved by
Half. Is LLM, so this is half BPS states. And it will become more clear when I tell you what the dual state is.
If it's half, shouldn't we not expect it to be black hole?
Yeah. So basically, this is a very, very good point. Right? So we are in a regime. So in the language that I think was already used by you, I think, yeah. So this is a regime where you only have graviton gas states, right? Then you can try to think ahead and lower supersymmetry. There will be, when you go to 116, there will be states that are for sure black hole states and graviton gas states. We are not there yet. Right here we just have graviton gas. Yes. In the outlook, I'll try to say a bit more about it. Yeah, please do interrupt me anytime. So one thing which is related to this novelty with respect to the previous paper is that if you look at this 5-dimensional metric, which is actually a solution of a gauge supergravity, 5D gauge supergravity. So this is how these people found it. And then this is an uplift formula that tells you how to construct a 10D solution from the 5D solution. This depends on Q1, and if you do a small Q1 expansion, it contains only integer power of Q1. But in this delta, there are also two scalars, and one of these scalars, which are again written in terms of this H1, has this form, R cosh d over dr square r square H1. If you calculate this and you expand for small q1, you see that this goes like a root q1 divided 1 plus r squared. So the 5-dimensional problem has an integer expansion in q1, but the 10-dimensional problem has also this root q1. These scalars appear here as a word factor, but they appear in a non-trivial way in the S5 metric. So this is the reason of one novelty that one sees when you look at Kaluza-Klein modes. They are sensitive about the S5. And so they will be sensitive about this scalar, which is not something we saw in the first place. Now, what is the dual interpretation of this geometry, this 10D geometry? So it turned out to, so let me call it OH. OH is, I mean, the dual interpretation has to be some local operator, because this metric describes a point-like object with a mass, not a tension, right? It's a mass and charge. So it has to be some local operator. And since this is half BPS, it's a local operator which is made just with one complex scalar. And it is a coherent state of this form. So X, Y, and Z are the three complex scalar of n equal 4 supergametes. So these operators, sometimes people call it O2, is the lightest operator in the n equal 4 theory. And this heavy operator dual to this geometry is the operator that is an operator that has delta equal j, right? Each scalar contributes 1, right? You have many scalars. So, okay, this is quotation mark. I think we discussed this point in Storybook. So, in principle, these are, okay, let me do step by step, right? This is, we do step by step. Right? So this is not a conformal primary because it's sum of the identity and then something of dimension 2, dimension 4, dimension 6. What I'm saying is that each of these terms has delta equal j. Each one of them is delta equal j. Now, what happens is that this alpha is related to this Q1. And the relation can be found by using a technology introduced by Skanderis, Taylor, and collaborator 20 years ago, which is precision holography. So you do a calculation with this state, you do a calculation with this geometry, and if this is a protected quantity, like a 3-point function of half BPS states, they have to match. And then you can do enough of this, use enough of these inputs to see that they match only if there is a particular relation between alpha and Q1. And this relation is the following. Q1 equal.
Sorry, Rodolfo, you mentioned that is half BPS.
Yes.
So is this OH is half?
Is half BPS because it's just made out of X. Right, so it preserves all the supercharges that.
If it's not an operator, how do you see that is? Sorry, if it's not a primary, how do you see that is? In which sense is half BPS?
Each one of these terms is half BPS.
Okay. Mm-hmm.
Separate. I mean, think about it. I mean, I do it very naively. Think about it as Q acting on something is a derivative, right? So I can apply the Q of this is the sum of the Q's, right? Linearity. And so this is actually the 32 BPS. This is half BPS. This is half BPS, right? So and it's the same Q's, right?
But they will have a dimension which increases.
They will have dimension which increases, but each term preserves half of the Q's.
So it would be a way to repackage all the contribution that you
exactly.
have of...
Exactly. If you want, you can think it in this way, as a generating functional that includes all these half BPS operator.
Okay.
Yeah. That's thank you. Now, so happens that if you take alpha to be an order 1 number, like 0.1, and you calculate the norm of this state, you will have a sum of many terms, right? Because you have the norm of these, plus the norm of these, plus the norm of these, right? And you can do a settle point calculation to see which term in this sum contribute the most. And you will see that the term, so let me write this as the sum of n. I think I want to do it like
Rodolfo,
this.
probably
Cannot
people
really see
can
it.
read,
Yeah,
can't
sorry.
read this.
Let me do OH as sum of n, 1 over n factorial O to the n. Right? The peak, the term here that dominates is the object that satisfies this. So what I'm saying, this is the standard calculation, right? You take the sum. The sum will have a lot of combinatoric factors. How many times you can contract all the x's. I'm calculating this, OH, OH. This will be a sum of n, right? The term here will have a combinatoric factor, how many times you can contract the x's from here and the x's from here, right? So that combinatoric factor is a lot of factorial. You can apply Stirling, and then you have an exponent. You take the derivative of the exponent, you set it to 0. So it's a very naive calculation, and that's a stationary point. So when you take n to be large, big N to be large, and alpha to be fixed, this state is a coherent state, but is dominated by one particular term, and this is the average occupation number. So you can think about this OH as we were saying, as a generating function, but as a heavy state, it's like just a big atom, right? With a lot of O2s. The number of O2s is not fixed, but is picked around this value here. And you see that this parameterization that we chose has a strange feature when alpha is √2. But that's just a choice of the parameterization, right? It's just telling you that when alpha becomes close to √2, the number of the constituents goes to infinity, and if you want to go beyond, the state is not normalizable, right? So that's just telling you, okay, small alpha is the regime where you have few constituents. Alpha around 1 over √2 is the regime where you have large charge. Right? So the number of constituents is larger than n squared. Very good. So now I told you everything I need about this part. Now I have to do the perturbation. What do I use for perturbation? So maybe I can erase this. So as perturbation, I just choose another operator. And in this case, I use a light operator, just one of the gravitons. So you can think about O3, trace x cubed, O4, trace x4 plus something, trace x square. But I can also think about things like trace x square y. Right? Y is just another scalar. So this is the focus of this. Initially, we just choose as perturbation the same operator that makes the heavy state, the simplest thing we could do, or another O2. Now, the idea is to extend to find a whole family of results. Well, the perturbation can be O3, O4, O5, O6. And then for each one, you have choices of different type of scalars. Now, to be precise, this calculation here, using this perturbation, would be a bit hard, because the equations described in the perturbation are not the wave equation of a scalar, because this object is actually dual to gravitons and Ramon four forms. So it's easier to use as perturbation Q for OK. Well, this K is 3, 2, 3, 4, is the Kaluza-Klein level of your operator. And this is dual to the axiodilaton, which in 10 dimensions is a scalar. So the equation that you want to solve to study black hole perturbation theory will be box calculated in this metric here. Tau is the perturbation, is the 10-dimension axiodilaton. What is it?
So this is the light and in the supermultiplet.
Yeah, exactly. This is the O2 supermultiplet. So at the end, it's easier to do this calculation, and then we find a result that holds not for this state, but for the state which has things like this. But this is the chiral Lagrangian in the supermultiplet that Agnès has in mind. But there is a word identity related to this Q, relating the calculation for these states with the calculation for these states. And the problem was kind enough to make it easy to integrate this word identity. So at the end, even with this detour, we can write the results for the chiral primary, which makes it a bit easier on the CFT analysis. Yeah.
Just for curiosity, if you would have chosen an orthogonal scalar like Z, would it get easier? Or?
Yes, I'll come to that.
Okay.
Yeah. So yeah, let me, no, this is a very good point, thanks. So what Christopher is saying is that in this Kaluza-Klein mode, you have the option to have as scalar the same scalars that appear in the heavy states, like X, or other scalars, like Y. Now, exactly as he guessed, it's easier to calculate a correlator where the scalars present are not X, are Y and Z. So this is reflected by the fact that this geometry, the SO6 break down in SO2 cross SO4. The SO2 acts on X. The SO4 is invariant. And so the Y and Z will be in that SO4. And there is a little novelty, if we have time, I'll tell you what happens when instead you put here things like this. Very good. So this is point 1 and 2 of what I wanted to tell, which is mainly the main message. So if you remember something of this, great. It's what I want. Now what I will do, I just tell you the technology that we used in picture, and this is a lot of what is underlining also the thermal correlator that Robin and Christopher studied, and the gravitational wave that Carlo will discuss. So maybe let me see whether there are questions on the setup. Okay, so
Maybe a curiosity. I mean,
yeah.
in principle, doing the calculation for the ones that would be dual to, as you said, gravitons or other more exotic objects. I mean, it's just a bit more complicated technically, but in principle, you could have also
in
brute
principle,
force that approach.
I think so. No, the answer is yes. And actually, the first calculation we did almost 10 years ago in a DS3 cross S3, of course, we start with the chiral primary, because it's the simplest thing. Let's start with the chiral primary. And the equation is a set of coupled equation with forms. It is not blocks. Then after a while, we said, okay, why don't we work with a scalar? And then everything was much easier. So I think in a DS5 will be the same, right? It's only when you do fluctuation around empty ADS that everything reduces to box equations with different masses. That's the work of Van Nieuwenhuizen, Kim, Romans. But now we are doing fluctuation around a non-trivial geometry, and it's not obvious that you can reduce just to a box equation. Here is the box, because it's a 10-dimensional deal. Now, how do you proceed? 3 steps. First step, you take tau. So it's slightly different from maybe what usually done for thermal correlator. We don't work with ADS5, we work with the 10-dimensional thing, ADS5 plus S5. Really n equal 4 super-Jan mills. So the first thing is you want to decompose from 10 to 5. So you take your tau, and you write it in terms of S5 harmonics. Right? Here I say k minus 2 because I had in mind these operators, right? Q4, O2, OK. This is trace F plus, and then I don't know, y to the k minus 2. Right? These 4 Q's take 2 of the y's and transform it to in F mu nu, F mu nu. Right? So if we do O2, which is the content of this paper, then you see the field is trivial in S5 and is sensitive only to the DS5 metric, which had this even power in Q1. Very good. This is step number 1. Step number 2. This is still, okay, once you get an equation for this big phi, it's still a PD, because you still have the 5-dimensional of a DS5. So we would like to get an ODE. So what you do, you decompose further on the harmonics of the S3 within the DS5. So you take this phi k, and these are the sums that Manuela was also writing earlier today. Right? And now you have, so this kind of Fourier transform, right? This is the sum of the momenta, which are discrete, as was discussing, and this is the frequency or energy. And then you plug it in the box equation, and you get some ODE for this phi. Now, the ODE that you find is ugly, because if you remember, I just erased, unfortunately, H1 had this square root. So you have an ODE with square roots all around. And then we said, okay, I don't know, it would be difficult to solve. Now, it's a common trick to rationalize square roots. Like, so you can introduce other variables, so change variable from R to Z. And maybe let me write this change of variable, since it may be instructive. So if you change variable from R to Z, all the square root disappears. So this has been chosen so that the Z is rationalizes the potential. And you get an Euler equation for any alpha. And this Euler equation is not confluent, so it's slightly different from Schwarzschild ADS, where you would get a confluent Euler. Here you get 4 regular singular points. And these 4 regular singular points are representing the space twice. So it covers, the Z variable covers twice the space. So this is the center of space. This is the ADS boundary. And one singular point is minus 2 alpha square, 1 minus 2 alpha square. And I will call this T 0. Very good. So this is the center of space. You see, Z equals 0 is like R equals 0. And when Z takes this value, the denominator vanishes. And so this is the infinity. So the usual ISCFT problem is giving you the boundary condition you want to impose in this solution. And the boundary, and this is another slight difference with black holes. Since we have no horizon, in the interior of the geometry, what do? You just ask for the fluctuation to be regular. the space, this metric is a fully regular solution, no horizon, no singularity, so you add something, perturbation, you expect that it will not mess up. So you would like to have a regular solution in this point, which is the center of space. And then what you want to do is to take that regular solution and write it in terms of local solutions at the ADS boundary. So take the phi k, and then as z goes to t, which means r goes to infinity, the solution which is now fixed by boundary condition is the one that is regular in the center of space. We'll have a non-normalizable term when it is expanded at the ADS boundary. And then we'll have a normalizable term, which one can calculate with this OIN technology. And let me write symbols that I will not define properly, but just to give you a flavor. So this is the normalizable term. This is just the behavior of the field around the ADS boundary. This object here does not depend on the ADS radial coordinate anymore, right? Because we went close to the boundary. So this depends only on the space-time of the CFT. And this object here, which I will call phi boundary, is the correlator Emanuela was discussing on the nose, right? So once you normalize this to 1, this is the correlator. So this is what you are calculating on the right-hand side. Now the correlator will have a different form from the thermal correlator just because this object is different, right? Now what do you expect? Well, you expect that when you look at the poles of these objects, the poles are on the real axis in energy omega. So they are normal modes rather than quasi-normal modes. Because there is no horizon, right? We are really describing a big atom. And the poles, so the poles of phi kb are nothing else than the conformal dimensions, the energy of these bound states, right? Of OH, okay. So the result will be naturally written in this heavy light channel as a sum of poles telling you how you can excite this operator by attaching the perturbation. Right? The perturbation can be attached and creates another state. Of course, this object here in general is non-BPS, right? So this is BPS, but they in general are not mutually BPS. And so you will have here all kind of the double particle Manuela was thinking about. Right here in this microscopic realization are, if you want, multi-particle, right? A lot of objects coming from OH, plus one coming from OK, and that's just one more particle. In general, this is a non-BPS object. You have anomalous dimension, you have couplings, right? That's the structure. So maybe the last equation I will write, and so I hope I have now time a bit to tell you about the conclusion in picture, in words, is the final form of the solution, this object here, which now I write for you after integration. So, yeah, this to be precise, I should have written this, right? Because phi, the heavy, sorry, no, I should have written this. Q4, okay. Right, so for phi, the perturbation is this scalar descendant, right? I will call psi the result of this object after I integrate away the word identity, right? So this should be this, U4, okay. Right, so this is phi is with the descendant, right? So psi will be when I integrate away the q's, right? Which I will not tell you how we do it, but it can be done. So this is the correlator of the chiral primary, between chiral primary. And, well, some factors. And it takes this form. So, okay, these symbols are clear. The time, the angle, the frequency, the spin. What is new are these two objects. Now, in a punchline, so what happens is that to solve for this Oin equation, one introduces an auxiliary description, which was introduced here in Trieste by Alessandro, Cristoforo, Giulio, and then also in Alba Grassi, and then people in Rome, Francisco Morales. Right? So the idea is you introduce an auxiliary description in terms of an n equal 2 gauge theory. And this n equal 2 gauge theory has a prepotential, and this prepotential allows you to define a period. That's the period, right? So this A is not, so it is like the hypergeometric, but this A, you cannot read it just by looking at the parameter entering in the equation. Right? In the equation, you will have the position of the poles and the position of the residues, right? In the hypergeometric, you find the connection problem solved in terms of exactly those parameters. Here, the idea is that the connection problem is solved by rewriting it in terms of this auxiliary parameter, which itself is determined by the parameter entering in the equation. So that's a bit of the game. So at the end, there is a single function, f, which in this problem is the Nekrasov-Saakashvili, so it's a quantum version of the n equal to 2 theory. This f is the one that determines both this guy and this guy. Now, a little novelty. So last time I was discussing this with the experts here in Trieste. In this application, when k is equal to, we found experimentally that at the end this residue is 1. And then immediately we said, okay, that will be a general feature of all of DS calculations. It will simplify everything and makes it easier. Then we do the first non-trivial extension, k equal 3, and we see this residue is not 1 anymore. So it was a bit of a fluke. And this residue here is related to derivatives of this f with respect to the parameters that appear in the equations. But, okay, that's what it is.
Is there a nice formula that you can write that looks more like...
Yeah, so there is, so you have to talk to the expert here, but there is a nice formula, and I want to devote the last 15 minutes to discuss this point. There is a nice formula to derive this f. So all these equations can be made very concrete. So you can calculate in a regime that I will tell you about this f explicitly. And then you can calculate this a and this r, and you can perform all these sums. You can perform everything. At the end, you get a result in terms of the cross ratio z and z bar, which I will tell you how it looks like. So the first thing I want to tell you in picture is what is this calculable regime. So the calculable regime is when, so this formula is still exact. We didn't do any approximation. Now, in calculating A and F and this residue, finding explicit value, you can do it in perturbation theory in T. So T is this quantity here. Now, if you go back, this quantity here was proportional to the average number of constituents divided n squared. So this is an order 1 number for heavy states, but nobody tells me that I cannot take it to be small, be 0.01. Right. This is exactly the small mu expansion that Manuela was telling me, because this is proportional to the mass, the dimension. So when you do the small mu expansion of, this is like the small mu expansion for this particular microstate. Now, at that point, everything is calculable. And what do you calculate? You calculate correlators of this type, or heavy, okay, or heavy, that capture these Witten diagrams. So this is the Ho heavy, and this is the perturbation. The power of T, exactly as what Manuela was telling before, is the number of gravitons exchanged between this part and this part of the diagram. So order T would be this. Order T square would be this, with 4 vertices. Now, you can see that combinatorically, in the heavy limit, right, when you have a lot of constituents, the probability for graviton to connect this with the same constituent is suppressed by the, with respect to the probability, the number of diagram, right, that you have like these ones. Right, because this goes like n choose 2, right? You have to choose 2 different. And if I do a loop calculation, it is only n. So this matches well with the idea that we did a classical calculation, just classical gravity, and we are not finding loops, hidden loops, right? So what we get is this connected 3-level calculation, 3-level contribution to the full correlator. In the heavy limit, this is the only thing which survives. If you want to erase these two and interpret the result as not OH, but O2 square, okay, which is something we did, right? Then you have to add by hand the term with the loop. Right? It's not captured by this term. Now, the form of the result is that once you perform all the sums and all these integrals, and here let me mention a choice that also was Christopher was mentioning, right? So this will have a lot of poles on the real axis. Then you have to tell me about this integration, right? So if you want to do the simplest thing, you can choose Feynman contour, and you find not the retarded, not the Witten, but the Euclidean correlator, right? The one that is smoothly connected to the Euclidean correlator. So you can do that, which means just take half of the poles when you do this Fourier transform. And you can perform all these sums. And then at the end, you can find this as a function of z and z bar, the cross ratio. So this has nothing to do with this z hat, right? This is just cross ratio in the CFT. And these functions, the type of function that appear here, are the generalization of the d function appearing at 3 level. The d function appearing at 3 level are this box integral with Lie 2, right? So this is for the result which has only one exchange. When you have 2 exchange, 3 exchanges, you get the the ladder integral. So the space of functions that appear here are just the ladder integral and its derivative. So this is particularly simple with respect to other CFT calculations.
Sorry, is it this similar to the weak coupling and equal 4?
I know that also there is the ladder that contributes.
Which is the derivative of the D function as well.
Yeah, I think the weak coupling is more complicated in a way that now.
Because there are more terms, no? But there is one which is always the ladder.
Yeah, but it's not only the ladder, right? So the full answer it contains other. The functional space is bigger, right?
Yeah, but the ladder is always derivative of D functions.
Yeah, I mean when you have, I don't know how to call the function for the two-loop ladder, right? I don't know. I don't know where are they defined for the two-loop. Okay, I just use the ladder diagram and as the seed. What happens in this strong coupling regime is that this is the whole thing you need. You don't have other functions. So for instance, I mean, you know very well, because you did it, the loop contribution, right? 2 loops, 3 loops, like 1 loop, 2 loops, 3 loops. You always have the ladder, but starting from 2 loop, you have also other structure,
but I remember
right?
there is a comment in one of these papers by Dolan and Osborne in which they write one function which is one part of the weak coupling, which is has exactly this property. So I was just.
I think the weak coupling there is a from what you should talk to Francesco next week. But there is one part which is determined by ladder, but then
there is
more.
pieces,
And what I want to say here is that there is only the easy part. Okay.
But I'm a bit still sorry to
sure.
asking, confused about the fact that you said that this is the correlator that you have there, no? This OH with the OK.
Yeah. So after so the phi contains the descendant, the psi is really OH. Okay.
But then this OH is the guy that you introduced before,
Yes,
which is not even a primary, no?
Yes, very good, excellent. So what happens is that okay, so if you think about, you have 2 ways of thinking about the same result, so the functional form is exactly the same, but you have 2 different interpretations. So if you think about it in this form, with many constituents, that's a heavy light correlator, right? Well, I set this to be at infinity and this to be in 0, right? And this is the result for the full exponential. So it is a non-standard object, right? This OH has not a fixed conformal dimension, but it's peaked around the value of number of constituents, which is given by this. Now, the picture suggests that you can have another interpretation, which you obtain just by erasing all the connection between OH and OH that are not involved in the exchange of gravitons. Right? They will just be 2-point function, free 2-point functions. Right?
Like factorized.
Factorized, exactly. You can take them away, and then you ask, can I give an interpretation of this object with here an operator with fixed conformal dimension, which is a multiparticle with just here O2 squared. Because I erased all the others, and I see that here I have 2 constituents.
So you are somewhat projecting on one of the components that you were writing before.
Exactly. So thinking about, as you said, as a generating functional, like the power of T will tell you how many constituents are involved, right? Okay, there is a bit of song and dance, and the answer is yes, you can do that. And you can find the part of the contribution which does not have closed loops. So it's not the full answer for that correlator. You have to add the closed loop. So for instance, for the O2 square, we could do it because you already did the 1 loop. So we went back to the liter and said, okay, you take this one, you add it to the 1 loop, and that's the full correlator. Exactly. With just expanding the exponential in sums,
Right.
and the power of t tells you what term in that sum you are contributing. It's just erasing this. And then, of course, okay, I will not tell you anything about this, but okay, you say, is it correct? Okay, is it really true? So you start doing some check by factorizing and extracting the 3-point function. So you do OPEs in various channels, and then you can extract 3-point function that you can compare with known results. They were derived not from this correlator, but other correlator with single particles. No, really for twist 4, twist 6, right? And then you can check that you reproduce the when these results are available, you can reproduce them.
You know, it's just rephrasing what you just said, but is it correct to think about it like so? If I look at so if I expand the exponential, then I have a sum of correlators. For example, at order alpha, I have like O2, O2, O2.
Yeah, I thought the alpha square because you take one or two from one and one or two from
So
the
you have
other.
a sum of bit and diagram, and at each order you can combine them to produce. So
Yes,
this is
that's what I was trying to sketch.
okay, okay.
Yeah. Very good.
For
So
example,
maybe,
at order alpha to 1, okay. But
very good. Now I come to that because yes, very good. That's about it. So if you do it for the perturbation is O2, as I told you, the operator is integer expansion in Q1, so it's only even power of alpha. So there is no this number of object here is equal to the number of object here. But when you have kk mod, this is not the case anymore. The operator is also contains linear order in term, linear order term in alpha, which were related to that scalar in the gauge supergravity. So what you are doing, you are calculating correlators of this type. Let me just have a picture here. So this is O2 square. This is O2. So this is order alpha cube, for instance. And this is O3 O2. Right, so this is a novelty. Now, you can think about this as an OPE limit of a 5-point function. Right? So if you resolve these two, right, move them away, it's a 5-point function. So another thing that we did in installment 1 is to take these 5-point functions which are known, and Joao is one of the experts, do the OPE limit, and then check that we reproduce the same result coming from this gravity calculation. Right? For the one with two O2s, right, O2 square, you should start from a 6-point function. There is a first result by Fernando and Gnocchi, but it's very hard to take the OPE limit. So we've not done that yet. I know people are working on that. Very good. So let me conclude maybe just with a couple of words of outlook. So one thing which I think will be interesting is to study the opposite regime. Instead of tau expanding around tau equals 0, expand around this alpha equal √2. That's a large charge regime. A lot is known in some cases, Christoforov, Zonka-Owen. So I don't know whether this geometric approach, this supergravity approach, can make contact with that. Another thing which is very interesting, and I think I was discussing this with Agnese last year, but we've now started looking at this more concretely, is instead of changing this object here only, also changing this object. Right? So look at heavy states that have less supersymmetry. Right? So your initial question, right? What about instead of half BPS states, quarter BPS states? We don't know of any black hole preserving quantum supersymmetry, but we don't know any strongly coupled result, I think. Maybe you can correct me if I'm wrong. That is non-trivial, right? So Agnese shows some non-renormalization theorem for quarter BPS states, but we don't know any correlator with quarter BPS states, which is dynamical and it's a strong coupling. So if this is a way to generate this CFT data, it would be interesting. And the final comment I want to say is going really a bit in the direction of the black hole regime. And so the idea is that here, when we take the perturbation and we look at the OP channel, heavy light channel, this state produced is still of a graviton gas state. Right? You just add an extra supergraviton and you produce an excited state. Now, there is a big development of people understanding states in n = 4 superunits, which are not of this type. And there is this business that goes under the name of fortuitous states. Right? Are they generically produced in these correlators? Right? If we do this OPE and we lower the supersymmetry of this object, right? So as external states, we still have graviton gas, but dynamically, does this probe, if you go in an appropriate regime, maybe when you have a large number of constituents, right? So that's the background motivation why we started this project, and then we keep doing something else because this is very, very hard, but sooner or later, hopefully, we'll go back to this problem. Okay, thank you very much.
Thank you, Rodolfo, for the questions.
When alpha goes to 1/4, what is the geometry interpretation of this? It's a geometric interpretation of this limit.
Yeah, so you see when there is this singularity, right?
Yeah.
When, so from the geometry, I just think that it's still an asymptotically RDS space because you can always take R bigger, so the size becomes larger, but you can also always take R larger than that size. So nothing should be really too...
But it's not like is Q related to any size? Like, do you have an ADS2 region in this case for this geometry?
Yeah, that's a very good question. I think no, because there is no black hole regime, right? So that's the point. One thing which I didn't say, but we learned from Carlos, is that the connection problem that is relevant for the large T alpha goes 1/√2 is more complicated than the one that I erased. Here I had the gamma, gamma, gamma. When you are in this large charge limit, you have a ratio of sums. So finding the poles is more difficult. And this type of problems somehow always appear when you have a strongly curved space. So ADS Schwarzschild of Christopher and Robin is the same type. The problem that Carlo will discuss will be confluent on, but the same type. So this problem here is slightly easier from the point of view of the connection problem, because at the end is just a dressed hypergeometric, where the gammas contain this period. So I don't know, maybe it's just random, but maybe the fact that it's technically more complicated is telling you that something special happens on the physics side more than on the mathematical side when you take this large charge limit, but speculation so far.
So then I guess we would say that although in this small t limit the mass of this this object is effectively small, it's not correct to draw an analogy with the regime of, say, the core perturbation theory of flat. In which the mass is, so m omega is small.
Very good. I think that's an important point. So the small m regime of mu regime of Manuela, I think it's this one is simpler than that. And the reason I believe is that this regime is smoothly connected to empty space. Right, so if you take alpha goes to 0, you add a regular solution that goes to a regular solution, which is empty space. Instead, if you take ADS watch, as soon as you have mu slightly different from 0, you have a causal structure which is completely different from the mu equals 0 term. So when in ADS watch you move from mu equals 0 to mu different from 0, you have two disconnected problems. Here you have two connected
Only the
problems.
faraway solution is you can pretend that there is no singularity.
You can
but
pretend,
in the closed region,
but-
you still see it for any n.
But when you solve the problem, you put boundary conditioning going at the horizon, and then it doesn't matter how far away you are, you have to take that, expand it to the infinity. Here, instead, is smoothly connected. So my bias, which I actually realized just preparing this seminar more clearly, is that every time you have this smoothly connected problem to empty, you have the easy connection problem. Every time you have something like Swatcher DS, which is not smoothly connected, you have this more complicated connected problem, which is the same as with
But why is the Schwarzschild problem complicated? It's just a stress tensor exchange plus the associated double traces. Just a
yeah, I'm not
single,
saying it's on the physics side. I'm just saying on the
single
on the
diagonal
math
exchange.
side, the formula they obtained is more complicated than the one. I mean, maybe you can correct me, but it has this ratio of sums of gammas.
But the order result here, if you do a CFT interpretation of it, like an expanding conformal blocks.
Yeah. That's very much the same. It's very much the same. So what I think Andrea is asking is, can we feel about it as stress tensor contribution and then double particle? If we now do this channel, right, the two light and the two heavy, all that goes. The interpretation is the same. It's just the couplings are different from the one you see in ADS watch it. I don't have a very good understanding why this difference is related, how it is related to the existence of an horizon or not. I think that would be an important point to clarify.
But it's
but-
not just the mass. I mean, I don't think that the coupling, like it's a stress tensor coupled to a heavy state. And
yeah.
it's because it's not a primary.
I mean, here you have also charge, so I think you have to you have to include stress tensor and currents. This is something I promise you I will do it. I haven't done it, but sooner. I think there is something one can learn from a more detailed analysis of this part. Yeah.
But maybe a related point is that I think that if you take the source sheet problem and you look at large spins, so you're basically forgetting about the horizon.
Yeah.
And if you forget about non-perturbative things,
That's the point.
then you get precisely the same.
Exactly.
So in that case, you can reinterpret the thermal thing as an heavy state, and then you get formally the same thing.
Yeah. But then in these sums, you neglect one of the
Exactly.
terms, right?
So you get the same.
Yeah, you don't have imaginary parts anymore, right? So it's when you have these sums that things become more complicated. Let me say just one more thing, is that we also, inspired by your work, so you can take this correlator and do a semi-classical Regge analysis, right? So what Manuel explained to you before, right? And then you would expect that this correlator becomes just a geodesics, right? Now a geodesics not in a DS watch, but geodesics in the geometry. And the calculation is exactly what Manuela said. You have to do this analytic continuation and then send Z to 1, right? And we just check, this is an internal consistency check, and it works exactly the same, right? So it's the same technology. So the semi-classical limit of these complicated functions is just captured by a geodesics in the background.
Very technical, Matteo. Just to understand, the T, the error, the alpha, how is it related in the Nekrasov Satas-Will with the Q?
Yeah, so this T is the coupling.
It
Is the coupling, right?
Perfect.
Yeah. So that's why when T is small, you have an instanton expansion, which is what I was secretly using. When T is 1, okay, you have to solve the whole thing, which I don't think.
Okay, it's gonna be the same, exactly the same, because of S-duality in this case.
No, but when it's a random value.
If it is a random value, no, but
Yeah. If it's that's what I want to exploit to now to understand the. But if it's a random value, okay, it's complicated. You don't have any expansion parameter.
Sorry, but even more technical again. So Can you give us a few details on how also let's say the mass parameters in the necras of
Yes, yes.
will
Not on
appear in terms of the n equal to 4?
Yes, not on the blackboard, but yeah. So what happens is exactly as you know, the numerators will will be related to the mass parameters, and now we have 4 regular points. So you have M1, M2, M3, M4, and
are they sitting in some particular symmetric?
there is maybe something interesting that I don't know why. So for instance, you can ask where this KK mod appears, and it doesn't appear in all masses, only in some of them, and it's always the case. So maybe there is some structure there, but now it's experimental. Another thing which is appearing when you take this KK mod, which I didn't at the end come back, but is the difference when you have the same scalars and different scalars. So when you have in this operator the same scalars as the heavy operator, instead of finding one OIN, you find a set of coupled equations. Because the scalars here can start talking to the scalar here. And we said, okay, end of the game. And I say, why? You look a bit better and you can decouple all this by summing them, and you find a set of decoupled OINs. And now you have different dictionaries, right? Different dictionaries. And if you want to reconstruct the whole correlator, you need to do calculation with different type of these perturbations. And that's what we are doing. That's why it's not. But it can be done, right? So now it's just a matter of being patient.
Yeah, but usually when, I don't know because you're using some operators that I'm not super used to, but when you have like these kind of point functions, usually you can decompose by some free parts and interacting parts.
Yes, all
and
that
the
is.
interacting part can be fixed by just looking at not at like orthogonal polarization, and then all the rest is just reconstructed by SO6 part. I don't know if this applies to the operators as well.
Okay, so we can discuss. So what happens is that that partial normalization theorem is true for all half APS. So that applies. It's free part, then this interligator polynomial, and then this the kind of dynamical part. The dynamical, so contrary to what happens when you have only O2s, the dynamical part still depends on the R symmetry. So you need a more correlator to fix the R symmetry structure. That's what we're doing.
There are more questions? No?
Sorry, just a quick announcement.